Welcome to the first content module of Practical Data Science. In this module, we'll try to answer the question, what is data science? But of course, this question will be something that we'll gradually answer over the course of the entire semester. So today, in this little module, we're going to basically talk about what practical data science actually means, what the title of this course actually means, and then we'll do a little bit of wrapping up. So I want you to imagine that you are working in the clinical sciences, and you have heard of a diagnostic test that is, quote, 90% accurate in detecting breast cancer. You've heard about this in the news. You've read academic research papers in which they present lots of encouraging statistics about the performance of this test. Maybe individuals around you are telling you how effective this test is. You acquire this test in a clinic in which you're working. Maybe you're the data scientist or the data engineer in this clinic, and you start experimenting with the test, and you notice that it's making lots of mistakes. So how can this possibly be? Is there something wrong with your implementation, or is there something else to this problem? So here's a little sort of hypothetical check. So imagine that we're going to screen 1,000 women in their 40s for breast cancer. That's what this test is meant to assess. Imagine that we already know from clinical theory, from our clinical colleagues, that there's a prevalence of approximately 1% of breast cancer in women in their 40s. We can call this the prior probability. So there's without knowing anything else, the chances of a particular woman in her 40s having breast cancer is about 1%. So this test we have, it can be defined in terms of its performance, not just in accuracy, which again we'll come to defining it a little bit later, but in terms of additional statistics that are very close to accuracy, and so close to accuracy that sometimes we kind of conflate the terms together. So very briefly, we'll talk about sensitivity and specificity, and we'll get much deeper into what each of these statistics mean later in the course. But for now, we can assume that we understand that sensitivity means that if the woman does have cancer, this test will detect it, will give you a positive result about 90% of the time. This is what we called 90% accuracy in the previous slide. This is a little bit different than specificity. So specificity of 91% basically means that we're going to have 9% false positives. And again, we'll define false positives a little bit more later as well. But for now, you can assume that what that means is when the test tells you that this is a positive case of cancer, about 9% of the time it'll be false. It'll be detected as cancer, but it's actually no cancer. This is a false positive. And so far, the statistics look pretty good. Intuitively, 90% sensitivity seems relatively high, and we can imagine it is. A 91% specificity also seems fairly high. We can assume that it is. And there we have it. So given these statistics, and imagine this woman takes a test and she tests positive for cancer. Just think about it for a moment. What is the chance she actually has cancer? A 90%? 50%, or about 10%, given the statistics we have here already. Okay, I want you to maybe pause the video, jot this down in your notebook, what your answer is. Maybe even write a sentence or a phrase about why you think it's one of these answers. And then when you do that, you can unpause. Of course, all of these numbers, the scenario itself, this is not medical advice. This is only, again, a reasoning exercise for the purposes of elucidating what we're talking about. So the problem is that we've kind of let our human intuition, the way human minds conceive of statistics, to fail us. And we've allowed it to fail us in a few different ways, maybe more than two, but I want to highlight two of them right now. The first thing is that we sort of conflated the idea of sensitivity with this particularly good test with kind of an outcome. So there's two probabilities, and we'll define a little bit more about what this sort of notation means later. The first one is the probability that if the person has cancer, then the test will give a positive outcome. This is the 90% probability we saw a moment ago. And we've kind of, in our minds, kind of conflated this probability with the probability that if there's a positive outcome of the test, then the person has cancer. And these are written in different ways, and these mean very different things. And we've kind of just conflated these in our minds as if they mean the same thing. And this is a very common thing in human kind of treatment of statistics. The second way we've let our human intuition fail us is that we've forgotten our priors, our base rates. Now remember earlier we had the statistic that only 1% of women in their 40s actually have this form of cancer. And we didn't really factor that in, probably, into our assessment of the chances of the woman actually having cancer if the test comes back positive. So what this means is that we've fallen into the base rate trap, by which even when the condition is very, very rare, a very good test with very high sensitivity and with very high specificity can still give us various false alarms. So I wanted to kind of visualize it here for us. I wanted to also mention that I often provide code for you in these slides, which you'll find on the website we talked about in Module 0. So a lot of the details here, don't worry about it yet. Like we haven't really talked about matplotlib or NumPy yet, and all this work that exists here. We'll get to it later in the course, but if you want, at any time you can download the code, you can run it yourself, and you can play with it and see what you get. So this graph represents 1,000 women. So each of these little rectangles represents a woman. Each of the X's mark a woman who has the cancer. And let's count them. This should be statistical, I think. So every time we run this, if you run the code yourself, you might get a slightly different distribution here. But let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 women in this sample of 1,000 women who have cancer. That's exactly 1% of the population having cancer. And then we have these sort of shaded areas. Those are indications where this really good test we have at our disposal indicates that the person actually has cancer. Okay, and sometimes it gets it right when the X and the shaded region sort of overlap. And sometimes it's these false positives. So the test says it's positive, but that's false. The person doesn't actually have cancer. And you can count some of these statistics yourself. So out of these 10 women who have cancer, 9 of them have the response that it has a positive result. So that's exactly our earlier test of sensitivity. 90% of the time when the person has cancer, the test comes back suggesting that they have cancer. But even with, you can compute this yourself, so the probability that somebody has cancer here, given that the test comes back positive, so in all these shaded regions, how many of these shaded regions has actually cancer? That's only about 9.2% of the time, okay? So this is a bit of an issue, and this is kind of the result of our misconceptions about statistics. So by the end of today's module, and today's just sort of an introduction to practical data science, you'll be able to explain what data science actually is in a sentence or a phrase or a paragraph. And probably when you explain what data science actually is, you're going to describe it in terms of what we call evidence. You might describe uncertainty and how evidence relates to uncertainty. And you might also talk about how we can use data science to make reasonable decisions. And those decisions are dependent on the uncertainty we have about the evidence we have at our disposal. We will be able to translate sort of real-world questions or tasks, similar to the one we just saw, into what is the target we're trying to make a claim about or predict? What data do we need in order to answer this question? And how can we make a claim that is actually checkable and falsifiable? So, practical data science. For this module, we'll talk about what it means to be practical and make principled and disciplined decision making under constraints. We'll talk about data. We'll talk about science. We will talk a little bit about base rates. I mean, I mentioned Bayes here. That's maybe we're getting a bit ahead of ourselves, but Bayesian thinking is a way to think about data and statistics that helps us avoid the traps we saw a few moments ago. We'll talk a little bit about evaluation and ethics, but really all of these are topics that will come up over and over again throughout the semester, throughout this course. So to begin with, I want to take the course itself and take its name, Practical Data Science, and step through each of these words and talk about how they relate to what we'll be learning in this course. So what does practical mean? What does practical mean in practical data science? Well, generally, we want to be able to learn more, we want to be able to do more in the real world, and we want to generally make better decisions. There's lots of aspects to these desires. Some of them are laid out here. One thing to conceive of is just sort of what it means to be practical in terms of how we build tools to deploy in the real world. And obviously we want to not rush out our tools before they're ready for the real world. And we'll talk throughout the semester about ways to make sure that we're doing things in a robust manner. But I just want to flag for a moment that it can also be the case that a good answer today can beat what we call a perfect answer next month. And to be honest, many times we're never going to have a perfect module. There's always going to be cases in which the module fails. Because we're doing statistics, we'll have to deal with these sort of trade-offs. So as we're reaching for the perfect tool, we don't want to delay all of the benefits we can provide to the real world by deploying really good modules sooner. We'll want to understand what is the value of information. This is a broad topic, but generally we're going to go out into the world and collect data, or others will collect data on our behalf. And sometimes this can be costly. It's a costly exercise. It's rife with all kinds of possible errors or risks. And we just want to make sure that when we're collecting the data, when we're computing these models, we want to do so in a way that, again, is efficient, is practical. It could run on hardware you actually have. It can run in a timeline that you actually have. So thinking more or less like an engineer, we want to make sure that we're not constantly seeking perfection at the cost of practical real-world benefits. We want to be able to start with good, smart, simple baselines. So throughout this course, we're going to be always trying to improve our approaches and improve our models and improve even our own ways of approaching problems. But we want to start with something we can still be somewhat comfortable with, something we can still be somewhat proud of. These are called baselines. These are initial attempts at models, and these are things that we ought to be comfortable shipping, hypothetically, if we needed to. Finally, reproducibility and maintainability can be more important or greater than having one-off successes. If it's the case that you have developed a tool, a statistical tool, a data science tool, that one day, using a particular configuration on a particular set of data, gives you, perfect performance or as near to it as you can possibly obtain. That might be very good for one day, but if you try to ship it and try to deploy it, say in a clinic, like in the example we saw earlier, without adequately ensuring that the result you're getting is reproducible, or that over time these tools that are shipped can be maintained given all kinds of changes that are going to occur in the world. Without attending to those things, you're very quickly going to become deeply embarrassed by massive failures. And these failures can be merely statistical, or they can be failures of real-world implementation. So it's going to be very important for us to ensure that while we're seeking perfection and improving the sophistication of our models, we don't lose track of the fact that we're aiming to deploy these models in the real world with real-world consequences. So I'd like you to pause the video now and think about this prompt for a moment. This prompt is to name one decision this term during this course where making a decision right enough and soon enough will matter. It'll be important to deploy something or submit something that is good enough and can be accomplished in a reasonable time frame. So however you want to interpret that, again, this is going to be not for marks. Think about it, write it down in your notebook, and then unpause the video when you're ready. Continuing on the topic of practicality, we want to just basically follow the pattern that we will take. We want to practice practical patterns. So generally what we have initially is a broad question defined potentially very loosely, but that we can translate into something that means success, and then we can take that criterion, which means success, into a very specific metric. So the example here from our previous breast cancer example could be like, well, we want to understand if we can detect breast cancer in women in their 40s. We can translate this question into something that means success. We want something that's accurate, that's correct most of the time, which is a very vague way of describing this criterion. But then we can break this down into specific metrics like sensitivity and specificity like we saw earlier. Once we have this metric, then we can lock in a baseline. We can have something like a linear model or a simple coded up heuristic that we can code given information from our clinical colleagues. This is something that might be inspired by recent successes, some of your colleagues in data science, or recent successes that have been reported in the scientific literature. We have a good baseline, and then we start an iterative process of trying to improve that initial attempt at a solution. We attempt to make that solution better. We want to have an evaluation method set up before we actually touch what we call a test set. We'll define this later too. But we'll have some data that we'll put into a locker and lock the locker and take away the key for a moment. And we'll try to do this iterative process of improving the baseline to a model or a tool that we really like. But we won't evaluate it yet on this held out data. We'll save that until we're really comfortable. We'll say, well, I'm finished iterating and improving the model. Now I'm going to evaluate how well it is on this other data that we haven't seen before. And we have this sort of approach, which again we'll talk about a bit later, because we don't want to contaminate the held out data. Rather, we don't want to contaminate our iterative process with the held out data. Imagine you have a situation where you're building a model and you're evaluating it according to this metric that we've defined previously. You test it on the test set, you find that the model actually doesn't work very well, so then you go back and start iterating again. This is kind of cheating, right? This is sort of like seeing the answers on an exam while you're studying, right? And going back and then studying some more. The performance you get on that test won't be indicative of the quality of the model, either the example in this example we're working through or the model of your own mind. So it's important that we have held out data so we can estimate how well our models generalize to unseen situations. We also want to document our assumptions and our limits, versioning data, coding results, standards of software engineering, and DevOps. We want to maintain in data science as well. Somewhat controversially, we might want to interpret tools. Might want to prefer tools that are interpretable or understandable when the stakes and constraints are high. This is not universally going to be the case, and maybe we'll come back to this topic later in the course. But imagine you have a model that is helping you make very high stakes decisions in government or finance or healthcare. And imagine you have no idea how this model works or what factors play into its decision-making process. If it's possible that you're going to be making high-stakes decisions for people, we might not prefer the so-called black box. We might prefer to be able to open it and look inside and see how it works, at least to some extent. Again, related to point 4, versioning everything, following good hygiene, good computer science hygiene. Having the data, coding, and results versioned and documented is going to be important. And we're going to want to understand how we can communicate our decisions and communicate our uncertainties to decision makers. We're not going to want to be, just hype up our model. We're going to want to understand what the trade-offs are, what the limitations are, and communicate that in a way that others can interpret it accurately. Fundamentally, what we're always after is the truth, right? This is going to sound cheesy, but we want to find the truth or approximate the truth as much as possible through our iterative process. And when we communicate it to others, we want to make sure that they understand what the truth actually is and communicate it in a way that's mature in that way. The second word in practical data science is data. So we don't want to, define this too much. I want to mention for a moment that data technically is a plural noun. Data is the plural of the word datum, D-A-T-U-M. So one datum is one data point, and a collection of data points is data. Sometimes we'll refer to it as a mass noun, but that's as maybe. Anyway, Merriam-Webster, clickable here, defines it as factual information such as measurements or statistics used as a basis for reasoning, discussion, or calculation. And that's more or less the definition we'll take in this course. The other definitions, which you're free to read yourself, kind of play into this. So information that is just stored on a computer that is transmitted over the network, is also data, but we're going to use that data to make decisions based on accurate reasoning, based on correct calculations. There's a great astronomer called Carl Sagan, who was a very important figure in the popularization of science. And we'll probably come back to more of his quotes throughout this course. He has one quote on the cosmos, which he studied extensively. But I feel that his quote applies equally well to data. So I've kind of paraphrased his quote on the cosmos to be that data is all that is, or was, or ever will be. Our feeblest contemplations of data stir us. We know we are approaching the greatest of mysteries. I think this is a good place to think of data also. It's a bit grandiose, I think, for what we normally hear in computer science, but I think it's going to be helpful for us to think of this not only in terms of the practicalities of data, but also like the meaning of data, what it actually means, right? It's our best attempt to reach for the truth, which we'll talk about in a moment. And it contains information somewhere therein that the search for is an activity that is more than just coding. It's the search for the truth fundamentally, which I think sounds cheesy, but it's also a true statement, right? We want data because data allow us to make valid, meaningful decisions in the real world. So speaking of data, I think it's helpful to develop the habit of thinking in terms of data generating processes. We should be able to ask the question, who created each value, each datum that we have? So did it come from a sensor? Did it come from a log file? Did it come from an individual? Is the individual data points actually the aggregate of a survey that we sent out and aggregated together? How did we do the sampling? Who did we sample? Who's in the sample? Who is outside of the sample? Is there any framing of the sampling, or is there any bias that might kind of translate into the decision-making process and potentially give us responses or interpretations that are incorrect? Are there any incentives to the data? Any reason that the values we have obtained might be strategically obtained or wrong in some other way? We're going to get into this throughout this course, but there's a good way to do data acquisition, data collection, and there's bad ways of doing data acquisition and collection. If you have a predefined idea of what you're looking for, and you structure the data acquisition process in such a way that you're almost guaranteed to get the answer you want, this is not really a valid form of doing data collection. Or even back to the idea of sampling. If you only sample data from people who share the same idea that you do about their conception of some concept, you're likely to get data that really kind of adheres to your pre-existing worldview. And that's just not really a correct way of doing data collection. Similarly, timing. So are the data we're dealing with from the 1950s and 1960s? Are we studying like immunotherapy data from 2018 or 2022? So when data is collected, among other factors, is going to be incredibly important for us. I would highly recommend being as curious as possible regarding how the data were gathered within reason. Sometimes we refer to this curiosity as skepticism, but occasionally skepticism has led to people having so open a mind that their brain falls out. They can be skeptical of valid processes and of experts in a way that kind of goes beyond what normal skepticism demands. So I prefer to think of this in terms of curiosity. So in a helpful, positive approach of curiosity, Can we just ask questions about where the data came from and think openly about how the data acquisition process could be potentially improved? So data kind of starts very raw and gradually gets distilled down into something that is closer and closer to what we want in terms of the scientific process. So we can think of data in some form as just the raw values. So the raw signals that are coming out of, say, a wearable smartwatch you have, or an ECG monitor across your chest. These data can be very noisy in all kinds of ways we'll get to. Somewhere within that very noisy data is what we would call information. This is somewhat more structured, it's somewhat more of a summary of the information. Maybe we've added units, maybe we've taken context into account. Maybe we've even kind of trimmed some of the data a little bit so that the signal we're looking for is more evident. And then, namely, evidence is what we're trying to extract. So we take the information that is sort of the true signal, and we want to evaluate it against a question we've predetermined, like we talked about a moment ago. So we're looking for something in particular. We have a question, we have a metric we have at our disposal, some kind of actual measurement, and then we evaluate the information against that evidence. All of this will be defined in greater detail throughout this course. We also want to have a rule that we can use to admit we're wrong. We'll talk about that in a moment, but this relates to the scientific process. So for example, you have raw lab values, maybe blood work has been obtained. You convert these raw lab values into something like statistics, maybe mean values, maybe confidence intervals with actual units. And then we'll convert that to something that we can at least relate to a question. So is this level we're measuring, this mean value, is it above some threshold we've predetermined in some predetermined protocol that needs to be flagged or needs to be followed up upon? So yet again, please take this prompt, pause the video, and write in your journal or your notebook. Think about any decisions you've made recently based on data of any kind of number or figure you've used, maybe based on your behavior, your diet, your sleep, your exercise, whatever it is. Think about that a little bit. Think about whether or not the data you looked at made you think you maybe want to change your behavior in some way or take some other kind of decision. And then think a little bit about whether or not the rule you used to think about that decision was something that you just came up with on the spot, or if it's something that you've previously noted as a threshold before you observed this data. And if you have time, think a little bit about what the difference is between coming up with a decision-making rule on the spot as the data comes in versus having a pre-existing rule behind the scenes that you're measuring these data against. And maybe there are third options that you might want to take into account too, but anyway, think about it a little bit and then come back to the video when you're done. I just want to mention that data are very messy, and that is not only okay, but it's actually sometimes a useful thing. Sometimes a little bit of noise in the data can actually help you clarify what the signal actually is. So noise, defined loosely, defined in greater detail in subsequent modules, can mean data that are missing, data that are accidentally duplicated or copied in some way. Outliers are data that are just data points that are just very different than all of the other data we have. Maybe there's some kind of encoding problem, or maybe the type of the data are mixed up. Maybe some of the data is in milliliters, some of the data is in cubic centimeters, and they actually are trying to measure the same thing but slightly differently. Generally in this course, we're going to try to follow something called the tidy data principle, coincidentally. The tidy data principle doesn't really solve those problems, but it can help identify them. And the tidy data principle is more or less how we structure our data. And with some exceptions, we're going to have every row in a table, a two-dimensional spreadsheet. Every row will refer to one data point or one datum, an observation. These will all mean the same thing. Versus the columns in our data table will refer to one variable we're trying to measure. So again, going back to the clinic example, you might have 1,000 women in your clinic. Each of those women will be represented by one row of data. And we'll be measuring lots of factors for each of these patients. One might be their age, that's one column. One might be blood work, that might be one or other columns, depending on what we're measuring. We might have columns based on their activity, other symptoms, and every new factor we're measuring will be one column in our data. There'll be various tools we'll use. So we're going to go in great detail in the next module about pandas. Pandas is useful for tables or spreadsheets of this type. And then we'll also go in throughout the course into lots of visual checks, lots of visualizations, graphs, tables, or figures that help us check things as we're going through the modeling process. So finally, we're talking about practical data and science. So what is science? I think people often think of this question, in ways that might feel somewhat cheesy, but to me, this is one of the greatest questions we have, and it's a question that we keep on having to ask ourselves. Fundamentally, at some point, it's about making falsifiable claims. So we need to be able to admit that we could be wrong. And this is, not to get into the history of science, but this is one of the chief ways in which science differentiated itself from other fields of inquiry into the nature of the world, of the universe, and so on. So, in some sense prior to science, but also in some sense alternatively to science, we might have a claim we want to make about the world. One approach might be to try to find evidence or reasons to support that claim. I think this because of this and this and this and this and this, and these are all positive things that help me support my claim. Unfortunately, this approach can sometimes lead to just claims that are either false because we've constructed things in a way that sounds plausible but it really is not true, or it can support claims that we can't really test whether they're wrong, right? It sounds good, but is it wrong? We'll have no idea of identifying that because we don't have any falsifiable claims. Again, not to sound like a broken record, if you know what that is. We want to be able to make falsifiable claims because this is kind of fundamental to the scientific process. How we'll do this is by seeking what we call severe tests. This sounds more severe as it is, as the name suggests, but basically all this means is that, well, if the claim we're making is false, how likely would it be that the test we have at our disposal would show that it's false? Okay. Sometimes in history this can be relatively straightforward. If a scientific claim about an eclipse is made, we'll just observe on the night when an eclipse is predicted if the eclipse occurs, and if it doesn't, then the claim that an eclipse is going to occur at this spot has been demonstrated false. Usually this test is not so black and white, so to speak, or binary. Often there's still shades of gray and there's still some uncertainty, even in the test that we're applying. Like maybe we tested for the eclipse at the wrong latitude of the Earth, for example. So we're going to need to be able to kind of quantify or measure what we don't know in order to kind of assess how good these severe tests are in falsifying our claims. We want to be able to guard against what are called forking paths. This is kind of similar to the example I mentioned earlier where we are running experiments and we're gradually trying to improve our models or our approaches, but we're going to kind of peek behind the curtain, so to speak, and kind of cheat in some sense by incorporating knowledge we shouldn't necessarily have, and have kind of contaminated our experimental process with information that shouldn't be part of the process. We talked about that a little bit earlier. Also, to be able to replicate our experiments, this is closely related to the engineering I mentioned earlier under the practicality sections. We want to be able to ship tools and software that work in our lab and also work in other labs or other clinics or other companies elsewhere. And I framed it earlier as an engineering problem, but this is also a scientific problem. Like it's a problem that would be solved both in the scientific realm and the engineering realm. If we make a claim that works on your computer but it doesn't work elsewhere, not only is it an engineering failure, but it's also a failure to understand what the data are telling us and to build these effective scientific tools. So if we get new data that we didn't have before, if we split up the data that we have in new ways, if we just tweak the aspects of our tools or the factors of our tools in some small ways, and then suddenly we get very different results, this can mean that we haven't really solved the scientific question appropriately. So, again, mentioning this previously in the engineering context, but now in the scientific context, If you have what appears to be a scientific claim that seems to work well in your lab, you keep on you want to be, I say, skeptical here. You can also frame this as being curious. Keep on asking questions, right? Don't tie yourself emotionally too much to the results of scientific outcomes. It's far better to be curious and ask more questions and find that the claim is incorrect than just blindly, claiming that these claims are universally true. And the scientific process requires iteration, just like practical engineering does, right? Maybe others who pick up your work afterwards will try to poke holes in your work and identify problems, but the point is that science is also an iterative, collaborative process. Okay? So in this course, we're going to be building lots of statistical models. We're going to want to make claims about those models, and we want to be able to have an evaluation process where we can essentially try to test and refute or refuse these claims. So I kind of mentioned this already, but just to kind of summarize it again, we're going to take our data and separate it into 3 different sets, usually. A training set, a validation set, and a test set. And we'll talk about this later. Each of these sets will be used in different contexts for different jobs, right? I don't want to talk about this too much at this moment. We'll talk about it again later. But fundamentally, we're going to want to have some test data held aside that we're not going to use while we're developing our models. We're only going to use that test data at the very last moment. We're going to want to have some kind of check we can apply. So when do we decide that we've iterated and improved the model sufficiently? When do we actually go on from that process, what we call the training process, to the testing phase? We'll do that with validation. So validation is a set of data we'll use to kind of tell us, okay, we're finished, the model is as good as it's going to get, now we can go and evaluate it. So our best results will often only appear after we've tweaked the model considerably. And the performance we're going to get is going to depend a lot on these different sets. And again, for I think the 3rd time in today's module, we want to make sure we're not leaking information from test into training. That's a no-no. So always be on the lookout for that possibility. So what is data science? It can mean many things. And again, we're going to iteratively answer this question over the course of the term. But data science can be thought of in a few ways. It is a discipline on its own, which brings in a lot of other disciplines. It brings in computer science, engineering. It brings in experts from whatever discipline you're trying to deploy in, finance, health, government, for taking evidence acquired from data into real-world decisions you can make under uncertainty. We're going to use lots of statistics and mathematics, and we're going to build up our skills over the course of the term. We're going to build up our computational and coding skills simultaneously, and often the math and the code are essentially the same thing. They're just 2 different ways of looking at the same concept. And then increasingly, we're going to acquire some domain judgment. This is a computer science course, so we're going to focus on that, but we're going to be talking about tasks and challenges and use cases in other disciplines like health from a few moments ago. Fundamentally, we want to make a positive change in the world. We want to make actionable claims that we are comfortable defending. And we're also going to develop the tools that we can use to defend our claims. So generally, the process is obtaining the data or defining what we need, understanding and exploring that data through some explorational analysis. We're going to measure data quality, how sufficient is the data to our needs. We'll build models. We'll start with simple baselines, and we'll get better and better models, or at least less wrong and less wrong models. We will evaluate those models according to metrics and different kinds of error analysis we'll have at our disposal. And then we will identify how we can decide and how we can communicate based on that evaluation to the real world, to stakeholders. And these are all going to be important topics, which I mentioned, I think, in Module 0. So finally, I think there's going to be various kinds of progress we're going to make in this class. So in some sense, data science represents the culmination of centuries of progress we've made as a species. So many fields have gone from kind of expert-defined approaches. Initially, these approaches might have been even somewhat superstitious, depending on the field. to the scientific process has developed expert-defined rules. So this can be like textbooks, in medicine that tell you, well, if the temperature is this and the age is that, and one more symptom is this, then perform this task. This is very similar to kind of traditional forms of coding, of computer science, decision trees, if then else rules, that sort of thing. But fundamentally, we've changed from that process to data science, acquiring data of a phenomena and using mathematics, statistics, data science to increasingly solve these problems better than ever. So this is true of agriculture, aviation, banking, education. Every field of study basically is now open to data science. So we've progressed as a species, and the goal of this class is to help you progress as an engineer, or as a software engineer anyway, who can ship data science tools, to progress as a scientist, to have more statistical tools and scientific tools in your tool belt, and generally become a more responsible, ethical data scientist. Just keeping with the topic of making progress, ideally, this course will help you identify sort of more appropriate forms of decision making in general, and often this relates to a large extent through data science techniques. So first, we have anecdotes. An anecdote is basically a single point of data, and this can be useful in kind of limited scenarios, but it is not necessarily going to actually provide you with actionable decision for the real world. So an example here is the anecdote that somebody says, my friend used X. X is the variable, not the website, and it worked. So not the website. You have the idea that, okay, someone tells you that someone they heard of, used a tool and used a process and it worked well for them. Okay. Now, first of all, that's a pretty broad, abstract claim, and you can ask yourself whether or not you even believe this particular anecdote. But even if this is true, even if the friend using X is true, and it's also true that X worked for this friend, that doesn't necessarily mean that this process X or this tool X will work for you or other friends or anyone else, really. It doesn't tell you anything about whatever X is generally. So anecdotes can be useful, like I mentioned. It can be useful for proofs by contradiction. So if you want to make a claim saying that tool X will never work, then this particular claim, if it's true, contradicts that claim. So at least it works for this person, this friend. So this proves that broad claim, but that's essentially one of the very few ways these anecdotes can actually be useful. Somewhat more specifically, we have shallow statistics. Here's where we've gathered data from the real world. We've computed some stats on them, so averages, variations, that sort of thing. We have a sample of data, and we're computing or communicating things like correlation and other statistics we'll get to later in this class. So the one problem here is that this is still at risk for data manipulation. We talked a bit about sampling biases earlier, maybe cognitive fallacies, maybe we're not interpreting the data as we should. I mentioned way at the beginning of this module that the probability of cancer given a positive test is very different than the probability of a positive test given cancer, and other kinds of errors we can make. So an example of shallow statistics would be something like 9 out of 10 friends recommend taking an action. So this is better, right? At least we have like some level of confidence, like 90% of your friends now are recommending something as opposed to just one. So it's a little bit better. But again, back to the same issues we had earlier. Is the sample biased? Like, are these friends of yours are they all taking, the red pill or the blue pill, so to speak? So maybe the data is sampled. Maybe, if you asked 90 more friends, then this 90% statistic might go down to 70% or 60% or 50%. So maybe the number of friends we've surveyed isn't really enough. So these kind of statistics we have to be wary of. It used to be the case. I heard an advertisement from way before my time. It was a radio advertisement, and it was for some brand of cigarettes. And the cigarette said something like 3 out of 4 doctors recommend this brand of cigarettes. I mean, like what was the question those doctors were asked is something that is not communicated to us, which is one form of bias. But it was a different time, and those 4 doctors might have been chosen specifically to answer the question in a certain way. So take these statistics as they are. Still better than anecdotes, and sometimes this is all we have at our disposal, but still not ideal. More ideal is having statistical measures of significance, some kind of deeper analysis. This is something where we want to test whether or not the statistics from step 2 are actually meaningful or not. So kind of statistics on statistics. And we'll talk more about this in weeks to come. This is exciting. This is something that a lot of people in the real world don't have exposure to. So you're gonna be able to learn what it means to be able to understand statistics in a very deep way. Over the course of this term, we'll produce business problems, or more typically, we'll acquire business problems. Like and business doesn't mean like corporate business. It can mean any kind of real world use case. We'll talk about data acquisition, data preparation, exploratory data analysis, modeling, visualization, deployment. And again, this is going to mean reproducible, interpretable, and decision-linked decision-making. So to wrap up, I want to highlight again that ethics is going to be a part of what we do. It's not just about our technical skills with code and our mathematical skills in science. We have to also be aware of fairness, who's included, who's not included, who might be harmed by errors that our tools are being used for or with. Because we're dealing with data, we may have questions of privacy. We may have questions of security. So how do we minimize the amount of data we're using for safety? How do we share data in a way that's safe? What kind of proxies exist? So variables might stand in for protected attributes. Maybe a protected attribute can be something like somebody's race or ethnicity. And maybe we don't want to incorporate that into our analysis, so we remove it. But it can be the case that in some cities, the neighborhood you live in doesn't tell you with absolute certainty someone's ethnicity, but there can be a higher degree of probability that someone comes from a particular ethnicity. This is becoming less of the case in many cities, but in many large North American cities, there might be like what's called Little Italy, which might traditionally have had more people of Italian descent living in that area. So even if you don't have a column of information with someone's ethnicity explicitly defined, if you have their postal code, that can be a bit of information that can be used to kind of re-identify somebody. And then other forms of transparency, like what are you gathering the data for, what are the sources, what are the limitations, and so on. Doing science well also means doing science responsibly. It's possible that we'll touch on some instances of science being done irresponsibly in the more distant past, but we always have to be on guard for this. Again, science is the best form we have for searching for the truth, and therefore we have responsibility to do it responsibly. The final takeaway I want to have here is that I want in this course for us, at the end of this course, all of us to be able to think like a scientist. So a lot of the concepts we've mentioned theoretically today we'll acquire through practice. I want you to be able to ship like an engineer, so to package your tools and your statistical methods in a way that you can be confident deploying in the real world. And I want you to be able to decide like a leader, have the skills to either make the decisions yourself or communicate information to other leaders in your midst, so that they can make the decisions effectively. We're not here to just press buttons on a black box, right? If you're thinking of using AI or machine learning as just like I'm just gonna send prompts to a chatbot that is not science, that's not responsible, and you're not going to have real world skills that are going to be important for you. So we're going to need to dig deeper. We're here to take messy problems, messy tasks, maybe ill-defined somewhat, to sharpen it into, I call it sharp math, but this also means concise and correct code. To take that math and that sharp, crisp, correct code into models that we can debug, and then to turn these debugged models into deployable decisions that we're proud to defend. Thanks so much. On to Module 2.